Hello, students. Today, in our online crash course for CSIR NET January 2022, class 3, today we'll be discussing the central force. Central force is a little bit a large topic, so we'll need two classes for that. So today, this is the first class of the central force part. Today we will discuss this very important general topics, and the next central force classes will be discussing inverse square law and the impact parameter problems. So I would request all of you to join the Google Classroom with this code if you haven't joined it yet. We already took two classes before. This is the third, and our slides, assignments, problem sets, notes, all are uploaded to the Google Classroom. So if you haven't, then please. So first, the very basics. What is a central force? Central force by definition is a force which depends on the radial distance only and not on theta and phi. So just imagine the spherical polar coordinate system. You have r, you have theta, you have phi. Now if any force does not depend on your theta and phi, so that depends only on r, and it will be in general directed radially. That is the central force. For example, most of the forces we occur in the nature, say gravity, say this Coulomb's force, this even that nuclear forces, all are central forces. So from the basic rule of mechanics, if your force is a central force, then watch here this basic definitions, then the torque r cross f should be 0 because r and r cap in the same direction, and if torque is 0, then torque is the rate of change of angular momentum, so then dl dt equals to 0, hence L will be a constant. Okay, that's my first formulation. To read the theory, you can read this Kleppner for central force, of course Goldstein. If you have time, I would recommend you not to go for this next 2 months. We have time, so just follow these notes and start problem solving. We have already uploaded the central force problem, so we won't discuss that problems today, but it is available already in the Google Classroom. Okay. So we have a two-body problem. We need to convert it to one body. This is the first step in every book of central force deal with. We assume that we already know. Then we'll this character. So this two-body central force becomes effectively one-body problem. The origin means that origin had shifted to the a common origin, which mostly coincide with the larger particles in our general discussion of sun earth problems, etc. Okay, so give a just glimpse to this theory if you want to. Now our first interesting first aim will be to have some general structure. So first is the equation of orbit. What would be the equation of orbit? That is you can derive it, but you need to remember it in the exam. So that is d squared d theta squared, which is operating on this 1 by r plus 1 by r. We might have a bracket if it's allowed. Let's see if a larger bracket is that is I wanted. So equals to mu r square by L Fr. F is the force. F is the central force, the magnitude of this. How this depends on the center. It may be 1 by r square, 1 by r cube, whatever. In the book, many books, it follows 1 by r equals to u. Many substitutes this, and if you substitute this, sorry, if you substitute this, so then it will look like more familiar. Expression. So what is mu? Mu is the effective mass. Mu is the effective mass. This capital L for angular momentum also used interchangeably with small l. Also some books use J. So all this L, L, J, these terms are used for angular momentum. Okay. The energy expression for the central force, any central force general problem will be half of mu r dot square plus half of L square by mu r square plus Vr potential. This Vr together with half of L square by mu r square, this is a very important quantity. This is called as effective potential. So I will highlight it in some way. Okay. So this is effective potential. Color is okay. Okay, we are wasting time here. Okay, fine. So then this is your effective potential, and this half of mu r dot square is the kinetic energy. So these are general formulation of the problem. Now we'll give you an example, important example. Say a particle is moving in a central force field that allows the particle to move in a logarithmic spiral orbit. So you don't need to bother about this. You bother only about this. If your r as a function of theta, that is your equation of orbit is given. So r is k e to the power alpha theta. Alpha is a constant, k is a constant, and theta is the variable. So r depends on theta by this equation. So in exam many type of equation can be given. So from this you know directly, just if I give you the equation of orbit, you just can find the force law. Well, that is very easy. But from this there will be another problem, determine, spelling is wrong. No, not wrong, there should be an space. So let's find r as a function of time, theta as a function of time. This means this. And total energy, what is the energy for the problem, or what is the energy for that central force. So these three things we can extract just from this equation. So the first solution, the force law, is very easy. We already know the equation of orbit. This we will use it there. So equation of orbit is this. Just you know r as a function of theta. Just put it there. Then you get force law. You always use L as constant because L is indeed a constant for property of the central force. So then you get F is like this. So F is proportional to 1 by r cube. So that you understand, that you have already done your BSc classes. Next will be a trick, that after getting the force law, if the orbit is given, then if I need to integrate and find r and theta, how would I proceed? See, we start from the definition of the angular momentum, that L is mu r square theta dot. That dot is missed. Oh, dot has been shifted. Okay, so L is mu r square theta dot. That is a constant. So if that is a constant, then theta dot can be written as L by mu r square. This capital and small l has been interchanged in my note many times, so I would correct it, but right now we need to adjust with this. So both small l and capital L have been used as angular momentum. So we just write theta dot as L by mu r square, and then you know r square as a function of theta, means r as a function of theta, just we put it out. So then we get theta dot, left hand side, right hand side we have theta. So theta dot is d theta dt. So we get d theta, we take dt there, and that function theta there. So then we integrate, and you will get it. You after the formulation of d theta and dt, then it's absolutely fine. So then you do the integration and find this theta in terms of the time, in terms of t. So just you do this from here, you do yourself. Next is very easy. We know r as a function of theta, so from equation of orbit we already achieved this theta as a function of time. Then you will get r as a function of time, as we know the relation between r and theta. Finally, energy. So how we will do this energy? U means you can write it as a potential energy, that is the force dr, if dr. So you just to get the potential energy, you just integrate the force with a negative sign. So then that is there, 1 by r square. So this is fine. Next is we know this theta dot is L by mu r square. So we rearrange this like in this way, dr dt, it is always used, dr dt equals to dr d theta into d theta dt. So hence you can get r dot as this dr dt is dr d theta. Dr d theta you know, because you know r as a function of theta, right? That is my basic structure was there, r as a function of theta, k to the power alpha theta. So you know r as a function of theta, so you can find dr d theta easily, and d theta dt you know this. So here you get r dot, so you got already u. So then what else we have? Then substitute into energy equation. What is energy equation? Energy equation is nothing but mu r dot square. Mu is the effective mass plus effective potential. U and V is interchangeably used as potential. So plus L square by no, sorry, plus plus what? I always get sometimes of yeah, L square by 2 mu r square. Sometimes problem. So just into energy equation and you get total energy is 0. Total energy is 0. That you do yourself. Well, this is our start of central force problems. We will proceed it into a circular orbit problem. So this was a first type, one type of problem. We can extract as many information as we can from the equation of orbit. Now what is special about circular orbit? What is the hic in circular orbit? Circular orbit is a special case for any, not only an inverse square force field, for any central force, and that circular orbit is an important things to be considered. So why? If something moving in circular motion, so you can understand, watch here. So the force, two things, the force, the central force between two particles should be equal to mv square by r, the centripetal force. So the force should be always equals to mv square by r for circular orbit. Yes. Then And for circular orbit, you know, the angular momentum always is tangential to the motion, as the momentum is just tangential for the circular property. So L will be always mvr. That is the circular motion property. In terms of effective potential, you'll see that the effective potential will be an extremum, either a minimum or a maximum. So the dr of the effective potential is 0, which will give you dvdr. I know you know that you will calculate dvdr is L square mrq, so mv square by r equals to dvdr. That will be the minus of fr. So that is we already told you. And the for circular orbit L is mu vr. That mu and m is used interchangeably, but it is always better to use a mu. So for every circular orbit problem, you just remember this. Force should be, the effective potential should be either minimum or maximum. In general, it's a minimum. Okay, L equals to mu vr, and this force should be equal to mv square by r. Okay, there will be a lots of problem there. So we do an example problem. Say we are given a circular orbit for a particular potential v equals to minus k by r cube. Well, so in each of the circular orbit problem, the potential will be given as a function of r. So then just with this information, we can calculate the energy angular momentum for the body of mass m. This is a very standard problem and very old problem. Always it has been asked. So what we do, we take the dvdr, that see this derivative of this potential is not 0, but 0 is ddr of v effective. So there is a misconception. This is not v effective, this is v effective is v plus half of L square by mu r square. So this is the derivative of this is not 0. So after doing this, we get this force is mv square by r. So del v del r is this. Then that should be, that is the force. This should be equal to mv square by r. So you know the derivative. So this minus sign, you sometimes you need to absorb it somewhere. So that's the magnitude of the force should be equal to mv square by r. So there should not be a minus there. So just a vector diagram. This side force, this side mv square by r. So sometimes the minus may come. So please be careful with this because we might have a misconception, because force is generally directed inward and our r cap direction is outward. So the force direction is always a negative for the attractive force. Okay, so then this 3k by r to the power 4, the derivative of this should be equal to mv square by r. Hence we get v0 square, that is the velocity at circular orbit, is 3k by mrq. Then we get into energy. What will be the total energy? Half of mv square minus the potential energy. So because for the circular orbit, we always know that how do you calculate? Remember the Bohr model of hydrogen atom, or simple your +2 level of gravity. So what you did, we did this v0 square minus this. So if we ask me that, sir, what is the relation, we used different energy relation and different energy relation. No bro, that this is not different. You can start with the general relation. For the circular orbit, your r dot will be 0 because your r is not changing. So if your r dot is 0, so what E remains? Half of the total effective potential is the E. So ER is that VR, and this is L square by, okay, sorry, I used a double. I used half twice. And this L square by 2 mu r square is half of mv0 square, which is the tangential velocity. So energy, this so this comes from this. half of mu r dot square plus vr. This is 0 for circular orbit. R is not changing, R is constant. This is the minus k by r naught q, and this is, you see, this is half of m or mu. This is mu v0 square, because your L is or mu, if mu v naught r naught. So there is a misconception. So this is v, this is r. So you might not say, sir, मुझे कुछ समझ में नहीं आया. Mu v naught r naught. That's okay. Okay. And that is already written there. So you get it. So then you calculate this. Effective potential at minima, circular orbit remains stable. Effective potential at maxima, circular orbit remains unstable. These we know. You can just have a big increase there in the sizes. Okay, we have spaces. For stable circular orbit, if your circular orbit should be stable, so then you get d square dr square v effective potential greater than 0. From here, be careful not to mess up with the signs. 1 by fr df dr plus 3 by r greater than 0 or less than 0. Sometimes there will be a confusion. I always face this confusion. This is my updated note I was working on there. This should be less than 0. This is more important. If we need to stable orbit, so the effective potential should be at minimum. So this should be greater than 0. Hence you try to find out, hence you try to prove this. If this is greater than 0, then this should be less than 0. I can copy. I can copy. So from this to this, try to prove yourself. I always messing up. Okay. Sign. Don't mess up. Okay. Now, next part will be, if there is a disturbance or something about a stable circular orbit, then as your effective potential is at minimum, then as this equilibrium is a stable equilibrium, then there would be a small oscillation about the stable circular orbit. So just a very basic small oscillation theory will give you that the frequency of small oscillation about a stable circular orbit will be 1 by m d square dr square v effective potential evaluated at r naught. You remember this from your one-dimensional study. You already studied it, this type of problem. Say if v is given as kind of ax square plus bx square b by x square, so you find del v del x at some point x0, that is your point of equilibrium. Then you find out this double derivative d square v dx square at x naught, divide by m, then take a square root. That is the angular frequency. Actually, this omega is angular frequency and nu is omega by 2 pi. So sometimes in answer, please check that if there is extra 2 pi, so this is actually an angular frequency. So then For this central force problem, we do the same thing. We'll work in the effective potential. So it's always the effective potential which matters in physics. So we'll deal with this. So that theory is not that tough, but I don't bore right now. I don't have that much time. Okay, example. So suppose they are given a potential, a very general potential, V equals to K r to the power n. Many problem will fit into this. Then you are asked to calculate the stable circular orbit of r0 and frequency omega 0. Sorry, frequency of small oscillation omega. So here it should be mentioned that frequency of small oscillation. Otherwise, you might not get it. The font need to always begin an equation. So this is not an equation, rather. Okay, so far so good. Now what we will do, we have effective potential K r to the power n plus half of L square by mr square. That is our effective potential. So as we know that we need to first find out the stable circular orbit, so which means effective potential is at minimum. So we directly calculate the derivative to find the stable circular orbit radius. So we get its L square by just taking a derivative mr square. So then L square by mrq, this becomes k n r to the power n minus 1, that is 0. Hence we get r0 is this. This is my the stable circular orbit radius. Then we calculate your if a double derivative of this, so d square dr square of that effective potential. This will calculate. This will give you this. Just check it out. Then we can use the value of r0. We have a r here, so we are going to calculate effective potential at r0. So just we put this r0 here. So then we get this, and hence omega. Using that formula. What formula? Remember it once again. D square V dr square effective potential at r naught. Take 1 by n. Take a big square root. Oh. So well, that is up to you. Do yourself. Check it out. So this is a very general problem. What we have right now. Yeah. For the above potential, justify if circular orbit is possible for all the values of n. This is a question. This is a theory. The theory is discussed as a theory in Goldstein. You also just do this. Justify if circular orbit is possible for all of n. Find the range of n. We need to use either way. In any ways we can use. Just do this. N should be less than of something. So this is a standard theory. Just do this. Done in many books. Done in Goldstein and many other books. Okay. Now we'll discuss something of effective potential, some geometrical structure of effective potential. Then we'll stop today's class. Today's class will be a little bit small. So I have some engagements also. I may show you some problems also. Let's see. We have, say this is a general structure of an effective potential. We generally use two special type of effective potential. So this is one type, this is another type. So what is the difference? This potential is minus k by f to the power n type of, where n is less than 2, when n is specifically less than 2, what happens there? Because see, your effective potential one term is L square by 2m r square, and your this potential is something minus k by to the power n is less than 2. If this is less than 2, then at the very small distance this r square will be dominating, and if it is greater than n by 2, then at very small distance this potential will be dominating. So this n less than 2 or n greater than 2 factor is very important. If n less than 2, the effective potential shape will be like this. R equals to 0 is diverges to infinity, and r tends to infinity, this will go to 0 in both ways. But for n less than 2, this will be say r minus k by r, or minus k by r to the power 1.5, etc. So as you see from the algebra, so there will be a minimum of the effective potential there, and this will diverge. So most of the potentials we deal with in our physical world is like this. There are some potential will be opposite to this, we will discuss. But this is a generally a Coulomb potential, this is generally a nuclear force potential, this is generally an intergalactic potential, this is a gravitational potential. Every effective potential, this type of things which our universe bounded by, this is like this. So say this is your effective potential. So for different type of energies, what will be the shape of the orbit look like? See, if the total energy of a particle is like this, in this position, above, far above, so then it just have a point, just have a classical region bounded point in left side, and right side there is no bound. We discussed this in our first class. So this does not have a bounded orbit, but yeah, a particle with an energy E1 can roam around in a central potential, but it cannot go more nearer to this point. This is a limiting point. Otherwise, if you go closer than this, say it comes here, then its potential energy could be higher than its energy, so it cannot happen. E2 may be 0 or maybe below this, well below this, the structure could be the same. Energy equals to 0. Anything above 0, structure will be same. But if energy is negative, means this is positive energy. This side is positive energy. Positive energy means we have does not have a bounded orbit. It only have a limitation. But if energy less than 0, then effective potential it cuts into 2 points. You can see this point and this point, it is cutting. So this region we can have a bounded, classical bounded orbit. We can have this. So this may be a elliptical orbit, as it will be a elliptical orbit type of, as there is a minimum, there is a maximum. As this is minus k by r, so it is an inverse square potential exactly. Then what happens when there will be a minimum of the effective potential? Of course, there will be a circular orbit, as we discussed. That circular orbit, the effective potential becomes minimum. So we'll discuss the inverse square force in the next class in very more detail. And below that energy, there is nothing, no correspondence with this thing, no interference with the potential. Okay. So this is the more available in nature type of problem. There is another type of problem when, as we discussed, that Vr is minus k by r to the power n, where n is greater than 2. Then at smaller r, this will dominate. This V will dominate. So V will diverge in negative side. This L square by 2m r square will be there. So here you see that if you have energy E2 like this, so what it will get? It will give you an unstable circular motion, unstable circular orbit, because it is at the maximum. Effective potential is a maximum. So you can get a circular orbit there, but that circular orbit won't have an small oscillation around it for a small disturbance. This will just crack. This is unstable circular motion. Now if we get energy lower than this maximum of effective potential, we'll get an bounded orbit. Here you can get an bounded orbit, as we see in this case. There will be a bounded orbit there. So there can be a bounded orbit there also if energy is less than the maximum of that effective potential. Here bounded orbit is possible if energy is greater than the lowest of that effective potential. So it can have a bound, upper bound R1, sorry, upper bound R2 or bound R1. So that's it. Now if a particle which is coming from outside, say coming from far away, is coming and interacting with this potential, it is generally will just, if the energy is less than that E2, if any particle coming from outside, it will just repel, it will just come and that's go away. But if a particle come with energy which is greater than this effective potential of this, then it can overcome the potential barrier and just go across away to this region. So if suppose a particle coming like this, less than, which is we'll discuss in problems, we have this problem, so we'll just write a comment there. So particle coming from outside is large R with V greater than V effective max, that E2 is V effective max, will overcome the barrier and get into inwards to the origin. That's it. We'll deal with this example next class. Yeah, next class we may deal with an example. Do I have a next class? I have a next class slide ready. Do I have that problem there? Yeah, I think I can. I should get this to here. I should get this to here. So I should discuss this. Okay, so let's say a particle moves in a potential Vr is minus k by 3r cube. This is a second type of potential, minus k by 3r cube. This is this type. So then for a given angular momentum, this L, find the maximum value of the effective potential. That is easy, just take a derivative. The effective potential will be like this, just like this. N is greater than 2. Remember this. Let the particle come in from infinity. It's coming from large R with speed v0 and impact parameter b. What is the impact parameter? Impact parameter is nothing but the distance. We know we do have a slide there. What is an impact parameter? Well, we should deal this. Where we will deal? We just put it there. So what is an impact parameter? So if this is an origin, if this is the origin, this is the origin, and particle is coming from the above height b from this straight line. So we have a phone. I'm sorry. Can I? Okay. So just if we have this b there, height b from this line joint, just a symmetry axis or whatever. you need to determine this properly. So if this is B, then angular momentum is mv naught B. So if angular momentum is mv naught B, the kinetic energy is half of mv square. So from the general theory of scattering, so you don't need to go with this. The impact parameter is B. Impact parameter is the distance between from this direct axis to that particle, and scattering cross section is pi b square. So how you calculate B, that is not a problem. Suppose you are here, some particle is coming directly towards you, then there is, I'm sorry, how can I make this silent? I don't know. Flight mode. Yeah, everything gone. Good, perfect. So if something is coming with just directly towards you, then there is no impact parameter. If something coming towards you but it is not hitting you, it will not be going to hitting you. The same thing I tried to do there. Is it is not going to hit you, then you just extrapolate the distance, and this is your B. Okay, and that mv naught B is the angular momentum there. At the first, just last class 2, we discussed the angular momentum concept of a particle coming in a straight line, moving in a straight line above the axis h. We calculated the angular momentum as mvh. So the same thing will apply there, and the kinetic energy is half of mv naught square, and there is Berthoud scattering cross section, etc. So we don't need it here, but yeah, we may need. Okay, let's see. So let the particle come from an infinity with speed v naught and impact parameter B, that is mean above from the just directly joining line above B. In terms of k, m, v naught, what is the largest value of B, B max, for which particle is captured by the potential. That is the key. The particle is captured by the potential. That is very important in our daily life. See some meteoroid or something or etc. is coming from a large distance, then it will be captured by our central potential, means it may hit, it may come to the origin, and if it's not captured, then it comes and go away, maybe this side, maybe that side, whatever. But capturing means it is overcoming. So the importance of the capture, particle coming from outside larger with E greater than V effective potential, that means it will overcome the barrier and may land directly to earth or wherever into the towards the origin of the central force. So for this way, because of this practical implications, we study this problem in depth. So the problem is, you are given a but earth, can earth have a direct capture by like this potential? No, this does not. But somehow the particle can land to our earth, and that mechanism we will deal with for inverse square law, but that is not inverse square law. So directly by this theory mechanism, the particle do not land in the earth. Okay, but okay, maybe in some other type of practical applications could be there. So well, just do the math here. So this is the effective potential is this potential is like this. Particle is coming in from infinity with this B. So for which is the largest B, and that is e.g. V effective R is L square by 2m R square minus K by 3R cube. Take derivative and make it to 0. Take a derivative, make it to 0. Check double derivative is negative or not. So we got this V effective potential maximum value. After taking derivative, to make it 0, just calculate it. Substitute this R value here. So that is math. And what if is less than the particle, if energy we already told is less than the V effective maximum, then the particle will reach a minimum value of R and lead back to infinity. But if it is greater than V max, then the particle will all the way start equals to 0 and will never return. The condition is captured and there is E greater than V effective maximum. Now for the particle at very large distance, L is mvg or mv naught B equals to this. So the condition becomes, then do yourself, then the condition becomes this. So V effective maximum we already calculated. So E will be half of mv naught square, so E should be greater than half of mv naught square. So just put it and do some calculation. Bmax is this, and the cross section for capture will be this. So do this math. If you don't do anything, then how can you will calculate, how can you crack CSIR net? You should this also do yourself. Okay, so now it's fine. We end our discussion of today here. You can give me a WhatsApp message or just email. We have our Facebook group, Facebook page, Jahid Teaches Physics. We have our Facebook group, Physics Guide. We have our YouTube channel just in my name. So okay then, this is our first part of the central force. We will discuss other problems in the central force, other aspect of central force in the second class. Most probably tomorrow, this will be our fourth class of the course and second class of the central force. Most probably tomorrow. I'm not sure of that. I have an engagement there. So please join that Google Classroom finally. And what else to say? Do practice the problem sets which already uploaded in the Google Classroom, and you might have it already before because I uploaded it in many places before that. So just keep practicing. We'll discuss more central force problems and more central force problem from the previous year problem sets also in the next class. Today's class is a general discussion of the central force. Okay, so thank you everybody for listening. Yeah, if you did not subscribe that YouTube channel, still you can subscribe it to get a direct notification from YouTube also. Okay, bye.